there's a huge effort right now, and there has been for a while, but it's really become much more widespread as we look to go back to the moon and really think about tackling Mars. Is what can you do with the materials that are there? What can you make out of them? What kind of resources are there? Because you don't want to have this huge monster logistics tail that comes all the way back to the Earth.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And without further ado, let's get right into it.
Today's sponsor is MatMatch. With MatMatch, you can find materials for your projects in their free database of thousands of metals, polymers, composites, and ceramics. For example, you could search based on a given mechanical property, such as hardness or tensile strength, or simply search by name to find more information about a specific material. You could also find and contact suppliers if you have questions about a certain material, and join more than 2 million engineers and designers who use MatMatch every year. To join, simply go to matmatch.com and start searching for free today.
Hello everyone. Our guest today is Dr. Sandy Magnus, a former NASA astronaut and now a professor of the practice at Georgia Tech in the departments of Aerospace Engineering, Material Science and Engineering, and International Affairs. Sandy started her career with McDonnell Douglas in the 1980s, where she worked on stealth aircraft technology. She then got her PhD in Material Science and Engineering from Georgia Tech in 1996 and was funded by the NASA Lewis Research Center, focusing on thermoionic cathodes. She then was selected to be an astronaut candidate in the same year before finally going up to the International Space Station in 2000. Thank you so much for joining us, Sandy. We are super excited to have you on the podcast.
Well, I'm delighted to be here, so thank you for the invitation.
Of course.
Yeah, thanks so much for joining us. I guess to start off, I know I'm super curious, and I'm sure a lot of our listeners are very curious to hear about your time in space, and we would love to hear about your journey to space. And then also, how did you end up at NASA? And more importantly, how did you end up with material science?
Yeah, I wanted to be an astronaut since I was a little girl, probably middle school. And I just decided to go for it and see what happened. And the journey that I took to get to NASA was not the one that I envisioned when I was that young girl, because I really didn't know engineering existed. I definitely didn't know materials existed, the field of material science. And I latched on to physics. So my first degree was in physics. And I got to college and discovered engineering. I'm like, oh, this is kind of cool. You take the science and you can go build stuff with it, and make things. That's kind of cool. So I got really interested in electrical engineering because I really liked electromagnetics and some of that aspects of physics. And so when I got my first job at McDonnell Douglas doing stealth technology, it was basically applied electromagnetics, and I did electrical engineering. And that's where I got introduced to materials, actually, because I didn't really, even when I was an undergraduate, run into the field of material science and engineering at all. But when we were trying to design these aircraft to hide from radar, the kind of materials you used on the aircraft and where you use those materials made a difference. And I got really intrigued with the study of materials because it was a combination of physics and engineering, and the fact that you could, look at the structure of a material, you could design a material to do things that you needed it to do, and the fact that materials were so foundational to every other kind of engineering that had to happen fascinated me. So I decided to go get my PhD in material science, and that led me to Georgia Tech. And then, of course, after I finished my PhD, I'm like, okay, I'm ready to submit my application to NASA and see what happens. And I got selected.
That's
When
awesome.
you applied to NASA, did you think you're going to get it? Or was it like, I'm just going to go for it and see what happens?
Well, that was my attitude the whole way. I'm going to go for it and see what happens. My plan was, I didn't know if I would get it, any kind of response the first time I applied. So my plan was to continue applying, like for the rest of my life until something happened or I aged out. I was fortunate in that I got selected for an interview that first time. And then you show up to interview, and they interviewed at the time in groups of 20 people. And that and it lasted for a week because they do tons of medical tests on you, right? So you meet on the Sunday, and you're in this room with 19 other people, and everybody is standing up and they're explaining who they are and giving, a short 5-minute bio. And I'm looking around the room going, okay, I'm just going to enjoy the week, because there were some really outstanding people in that room. And I figured at the very worst, I was here for the interview. They could now match a face to the paperwork that they had, and that maybe I would have a chance the next time. But I was lucky. They picked me up that first time. And so the rest, as they say, was history. And I started in August of 1996.
What was the process like of preparing for the trip to space?
Yeah, so when you show up as an astronaut candidate, which is what you're called when you report to duty that very first time, you basically go into general training. So all at the time when I joined, of course, we were just getting ready to fly space station. So we were learning everything about the space shuttle. We were learning everything about the space station. We were, learn a little bit of other stuff. That took about a year and a half to do all that. And then you're eligible, once you get out of like boot camp, if you will, or basic training, then you're eligible for a flight assignment. And so now you're in the queue and you're waiting to get your first flight assignment. You have no idea when it's going to happen, but you're like so close, right? When you get assigned to your first flight for shuttle missions, the training was about a year. So you get assigned a year ahead. And then you train specifically for what you're going to do on that mission. When you get assigned for space station mission, nowadays, the space station training is about 2.5 years. They've really been able to make it more efficient over the years. When I was training for space station, it was a 4.5-year training flow. Because when you train for, it was like getting a degree, right? When you train for a space station, you tend to have to be a jack of all trades. So that means you got to absorb a lot of information, and it's global. It's all over the world. I traveled to Russia and Japan and Europe and Canada for that training.
Wow. Okay, so we're going to get to the question that I feel like a lot of our listeners are waiting for. And so since you spent half a year in space, we are wondering, what was that like? Can you tell us about your time in space and the flight to get there?
Yeah, I flew in space 3 times. 2 of them were short duration missions. We just flew the shuttle to the space station and helped assemble it or do logistics or whatever. And then my long duration mission was 4.5 months. They're completely different experiences. If you can imagine, you visit Hawaii as opposed to living in Hawaii, right? It's a completely different experience when you live somewhere. So I lived in space for 4.5 months, and that was really very special. You adapt to a whole nother level. You get very proficient at what you have to do. You never get tired of looking out the window and watching the Earth go by. It was just a really spectacular experience for all you engineers out there. Newton's laws rule your life. Everything that you have to do, you have to sort of internalize how Newton's laws work, and you do internalize it. It's a great place to teach physics.
So as someone who doesn't like roller coasters because of the dropping sensation, would I make it back to Earth alive, or do you think that I would be too afraid on the dropping back into Earth?
Yeah, so don't go on the vomit comet if you don't like that feeling, because that's actually a worse experience. Because on the vomit comet, which for those of you who aren't familiar with it, it's this airplane that we train for 0G. So it basically flies in these up and down curves, these parabolas. And so when you're at the top and you're just coming over the top of that turn, you have about 20 seconds of microgravity. But when you get to the bottom and the plane pulls up to go do the next parabola, 2 Gs, right? So if you don't like roller coasters, you would hate that. But when you're in space, of course, it's microgravity or essentially zero gravity all the time. So you'd be fine. Okay. And then when you come back, it's a very slow buildup of G's. So it's not the kind of jerking around that you get in a roller coaster. So I think you'd be fine. It's totally worth the trip to go find out.
Hopefully, maybe one day. But yeah, I guess as a scientist, and you're talking about these Newton's foundational laws, I think it's like a lot of our dreams to make a profound impact on our field and to experience things and find new revelations that other people haven't. And I think that in space, you probably had an experience that only a handful of other people have gotten to do experiments and try to figure out some of our foundational laws in greater detail. Could you tell us about your time as a scientist on the space station?
Mainly my role on the space station was to help other scientists accomplish their goals. There's a whole system for how investigators get science experiments into space, and we're up there helping them operate them or providing feedback to them. So more or less like a glorious lab tech when I'm up there. But there's all kinds of different experiments that people are doing on the space station, from fundamental materials, which we can talk about in a little bit, to combustion, to biology types of experiments, plant growth types of experiments. There's just a plethora of investigations going up there. And I think one of the things I enjoyed while I was living on the space station was a chance to engage across this whole broad field of science. And I wasn't just, stuck in my lane. And that was really brilliant.
Did you feel like you became a jack of all trades when you were part of those experiments?
Oh yeah, even just living on the space station, I was an electrician and a plumber and a mechanic and a lab technician and an arm operator and a trash lady and a logistics person. I mean, you do everything when you live there. I mean, just think about what you have to do to keep your house running, right? Mm-hmm. We have to do all that ourselves while we're on the space station.
Did you know how to do that on Earth? Or I bet now you do, right?
I knew how to do some of it. Of course, they train us really well, especially, if we're going to engage with some of the equipment up there that's pretty technical. And we have procedures and instructions, and mission control keeps an eye on us. But we get sufficient training that even those people who haven't done some of that type of work can get familiar with it.
Right. And now I bet you don't have to pay for a handyman when you're at home.
Yeah, it's more a matter of, do I want to do this, or is it easier to have somebody come in?
Right. Yeah, you have to do it when you're up there.
Yeah, exactly.
But yeah, so we do this thing where we ask our followers on Instagram and in our Discord community if they have any questions for you. And one of our listeners, Alice, was curious about how the properties of a given material change in space compared to on Earth. So I was wondering if you could highlight some of those unique differences and how a materials engineer working on space systems would adjust to those differences.
Yeah, so one of the things that's really interesting is that without gravity, the behavior of fluids is markedly different, right? So surface forces starts to dominate the behavior of the fluid. And so everyone's probably all seen astronauts with, floating spheres of water in front of them. Well, that's because that's the lowest surface energy shape that a liquid can form. So they naturally form spheres. There's a YouTube video out there, I'm pretty sure, with me with a glove of water on my hand, because the water wets my hand and sticks to it. Now, if I shook my hand fast enough, I could overcome those forces and flowing the water around. But how you move fluids around is, you have to really think about it, right? A shower does not work in space, because what makes a shower work? You turn on the faucet, the water, goes to the shower head, and then gravity makes it fall on your head, which is a beautiful thing. I missed taking showers while I was in space. But if you had a typical shower in space, like we designed them on Earth, you turned the faucet on, the water would be coming out of the shower head, but it would be sticking to the faucet, and the bubble of water would just be getting bigger and bigger and bigger, right?
Wait, Sandy, so how did you bathe, like
sponge baths?
Sponge baths? Okay.
Sponge baths, yeah. So fluids behave differently. And then there's been a lot of experiments in materials solidification. If you think about alloys and other mixtures where you have a couple different metals or elements coming together to form an alloy, in gravity, the heavier metals, the heavier elements tend to sink, and they do all kinds of magic, on the ground to try and keep a heterogeneous mixture happen. And it's a little bit different in zero gravity, how those dynamics play out, how the solidification works. And so that's another thing. And a lot of work's also been done in colloidal, like really, really small materials in suspension, and what happens with that behavior as well. So those are the more materialsy. But if you think about the human body and cells and viruses and things like that, those are different kinds of materials, and they're immersed in fluids, so they have different behaviors as well. And so these are all the things that we're studying up there.
While you're up on the space station, what do you think your favorite experiment was to either help with or watch happen?
Oh gosh, well, what we all enjoyed when there was a experiment up there that was a plant growth experiment. because it was so lovely to have something living and green on the space station, because it's a big machine and you're living in the machine for months and months and months, and you kind of miss the color green and, living plants and things like that. But one of the experiments that I really enjoyed participating in the most was this nutrition experiment. So there was a principal investigator at Johnson who was studying how the biochemistry of the human body and how that changes. Does being in zero gravity affect what your minerals and nutrients you're absorbing from your food? And so, I had to keep a daily log of what I ate and what I drank. And then every month I took my blood, froze it, and urine the same. And so he's been studying for, over a decade now, how does our nutrition and our biochemistry change in space? Because to me, that's fascinating. It gets down to those reactions that are happening at the cellular level, and where fluid again is behaving differently. So how does all that affect your body on a macro level? To me, that's just fascinating. I am not a life scientist, but that's something that's always fascinated me.
I think I read online that even NASA is looking into 3D printing food items with greater quality and nutrients. Is that something that you know a little about? Like how exactly would that work?
Well, I don't know exactly how that works, but I will tell you that the people in the food lab, that's a whole nother branch of science that's really fascinating, because they have to make sure that for example, I was chatting with one of the women who work there. Well, we do food tasting and pick our menus for shuttle missions. For station missions, you kind of get what you get, but for the shuttle missions, we can pick our food, right? And she was describing to me the experimentation that went into making the meatloaf, because they had to, make the recipe, then they had to dehydrate it, right? Because that's how it goes. And then you have to rehydrate it. And then when it's rehydrated, it has to have all the same nutritional value, and it has to have taste and be palatable, right? And it needs to have shelf life, because, for some of this food that we send up, that's contingency, it may be up there 6, 7 months, years, so it was really fascinating to me, all of the science that was going into just producing food.
Quick question then, what does that type of food taste like? Like how distinct is it from the food we eat today?
Yeah, so the meatloaf was horrible, but I don't like meat that much anyway, and I've never liked meatloaf. But some of the food is actually really, like shrimp cocktail, super good. And then they dehydrate the shrimp, right? So you have to rehydrate the shrimp, which is in a pouch with the cocktail sauce. So you put the water in there. The trick is to let it sit for 15 minutes and it's good to eat. No, you need to let it sit for a couple of hours to let it get nice and dehydrated. But that's very flavorful. The soups, some of it comes as meals ready to eat, so it's just in pouches, right? And it's ready to eat. So the soups are pretty good. The cream spinach is pretty good. I mean, there's some really good food. Now, what happens when you live on space station is you get the same menu every 10 days. So what you miss is variety. And what you also miss is crunchy and fresh. Because again, if the food has a little bit of liquid in it, just like the water on my hand, it'll stick to the spoon. And you can eat it without making a mess. But if you have dry stuff like a bag of popcorn, bad news, right? There's you open a bag of popcorn and poof, it goes everywhere. Or a bag of potato chips. And think about it, potato chips could be actually pretty dangerous because they're sharp. And now you've got them floating around because they're not falling to the floor.
I had never even thought that a bag
No,
of potato
nobody-
chips
Dangerous.
was the most dangerous thing on the space station, perhaps. But that's awesome. I guess one last question about space, and then we can move on to material science. Is once you got back down to Earth for your first day, like, did you do everything you missed, or like, what were the things you missed the most?
Well, I missed, after being on the space station for 4.5 years, I was super excited to go outside. I remember when we landed and they opened the hatch. We were in Florida. We landed in Florida and we opened the hatch, and that fresh, well, it's Florida and it's muggy and it's summer. So maybe it's not fresh, but to me, it was fresh air, right? This fresh ocean breeze, just smelling of Earth, that damp, earthy, musky, little bit of salt water smell came in. I'm like, oh my gosh, that's fresh air. And the guys who picked me up from the space station, they'd only been there for 12 days, and they're all looking at me like, what's the big deal? It's like, you don't understand. This is the best air I've had, and it's fresh. And just going outside and being around trees. I love being out of doors, so I really missed that. So it was beautiful to be back on our planet. I think people take our beautiful nature for granted, and you really ought not to, because it's really, really special.
I know David said that would be the last question, but that reminded me. Did you end up ever doing a spacewalk? Did you leave the space station?
No, I was trained to do spacewalks for the ISS mission that I stayed on, but we didn't really need any. There was no emergencies that came up that required us to do one. And on my shuttle missions, I was usually the robotics person supporting the space station, or spacewalkers. So.
Yeah, so you taught us about your amazing time in space, but there's a lot of material science that goes into getting you up there and then keeping you guys alive up there. So we're going to talk about a lot of applications, but the first one is when you go up in the space shuttle, one thing that you probably don't think about for our listeners is that the windows on the space shuttles have to be very particular in how they're made due to numerous amounts of factors. Could you tell us about how the material selection and processes go into making the window?
Yeah, actually, it's materials and engineering all combined, right? Because there's a lot, especially the ones at the front of the orbiter as we go up, because it's right in the airstream, and so there's actually several panes of windows. So they have redundant. First of all, they create redundant, but then they had to figure out the structural loads that the windows needed to withstand, and then what kind of material can withstand those loads. Because the inner windows are not structural; they're sort of there in case a piece of debris penetrates the outer window, so you don't lose your pressure seal, right? So they had to figure out the structural requirements, and then also you have to be able to see out the window. So depending upon the thickness that you require for structural purposes, you need to make sure you got optics so that they're useful as windows. And then they had to think also about re-entry and the temperatures, but that part of the orbiter doesn't really see huge temperatures, but it's a factor. And so these are all the questions that if you're the materials person or the engineer trying to figure out how to do windows, these are all the factors you have to take into account.
Okay, and so like going off of the micrometeor hits, we can talk about the hull of the space shuttle as well. You need to minimize the weight while also being able to handle those extreme environments and potentially those extreme impacts that come along with space travel. So how exactly did material science play a factor into that? Because I think aluminum is used quite extensively in these space shuttles.
Yeah, the skin of the orbiter, the shuttle, is pretty thin aluminum, right? So then you go back to, okay, then how are you carrying the loads through the structure? What materials are you using for the spars and the beams? What's the sequencing of that based on the material you're selecting? How close do those spars and beams have to be together? How's the aluminum skin taking the load, or is it, which just means how are you connecting it? The metals have to be similar so you don't have corrosion issues. You have to attach for the bottom of the orbit, you got to figure out how to attach the shuttle tiles to them. I mean, all of these questions you have to think about as the designer, and what are the materials that you have available? It can't be too expensive. Cost is something engineers you don't learn in school because you're learning about all the equations, right? But cost is an issue. How are you going to process it? If you have a complex curved part, can you stamp it? Do you cast it? Do you mold it? Now we've got 3D printing, but can you get the right tolerances and the right structural properties? So these are all the questions you have to ask yourself when you design something that's complicated. Well, anything really, but in the space shuttle in particular. But the skin is real thin.
So when you talk about cost, one really popular way to tackle cost now is like the reusable space shuttles. So when we talk about reusable space shuttles, do we have to completely do a new hull, or how exactly can we reuse things that have gone to space?
Yeah, so we're not really reusing space shuttles at this moment. We're reusing capsules, and then SpaceX is reusing boosters and rockets, right? That doesn't mean we won't have a reusable winged aircraft in the future. Sierra Nevada is building a winged aircraft that's kind of about a third of the size of the shuttle, which will also be reusable. But the people who are designing reusable have to really think about, again, what are the loads that the vehicle's taking? And, you have to maybe then add up, okay, if I'm going to fly this 10 times, I'm going to experience those loads 10 times. So I have to add a factor of of safety or another factor in there. And you've got to do all those calculations and figure that out. And that may or may not change the kind of materials that you might want to use based on how many reuses. The biggest issue is the thermal protection. As you come in, what kind of a thermal protection system do you need? In the Apollo days, they used ablative systems, which meant that it was a sacrificial layer on the capsule. And as you came back through the atmosphere, it burned away. And as it burned, and you just put more of it on than you needed so that it never got down to the aluminum skin, right? But that's not good for reuse. I mean, the shuttle had the tiles, but those were extremely effective, but they were a great material system, but you had to constantly replace them and treat them with tender loving care. So it's not a robust material system. And so what the companies nowadays have been investing in is what kind of thermal materials do we need to create that are like a shuttle tile and that they're not ablative, but they're not so fragile or sensitive, require so much tender loving care, so they're more robust. And those are the kind of systems that they've been investigating and trying to employ.
When we talk about the shell, we're protecting the aluminum, and I guess the main reason is because if the aluminum wasn't protected, it would cause catastrophic failure due to aluminum basically melting. Is that correct?
Yes, that's exactly what happened with the Columbia accident.
Gotcha.
Almost 20 years ago now. In this case, it wasn't a tile that got compromised. It was the carbon-carbon wing leading edge, which was a material that was designed to withstand that, thousands of degrees of heating that the wings must withstand to re-enter. And what happened, so that material is very brittle. And so a piece of foam actually fell off of the orbiter and got knocked off of the tank because the tank was super cold. And so the foam cracked. And so a little vibration during launch, the foam fell off and it hit the wing leading edge. And you wouldn't think that a piece of foam could damage something like a carbon, but because it's a brittle material, it caused a crack. And so now during reentry, some of that hot gas penetrated through that crack and just melted the aluminum spar that held the wing, and the whole shuttle destroyed itself. So material selections are important. You have to understand the environment they're working in. What are you going to do with the thing you're trying to engineer? And you have to be very smart about what kind of materials you're going to use.
Absolutely. So then what steps were taken after that accident to, I guess, prevent that issue from ever happening again?
Right. And so here's where cost became an issue, because we couldn't really re-engineer the whole wing, and that carbon-carbon technology that is on the leading edge of the shuttle was pretty state of the art even today, right? So what they did was we went and looked at the foam on the tank, the external tank. Think of the external tank as a big thermos bottle, right? The liquid oxygen and liquid hydrogen that were inside there, which is the fuel for the shuttle main engines, had to be cooled to super, 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 super cold temperatures. And that foam was basically insulating. And so they went back to look at how can they engineer that material, that foam, to keep it insulating, but also adhere it better to the tank so that it wouldn't be as apt to fall off. And then there was all kinds of other mitigations about just making sure that we inspected the shuttles better before they came in to make sure there weren't any cracks and things like that. But that was fundamentally, that was a materials problem at both ends of it, right? The foam and trying to get that to have more integrity and stay on the tank. And then really understanding, a lot of work was put into really understanding the wing leading edge carbon-carbon material and what actually it took to break it under what circumstances. So it was more of a characterization effort, whereas the foam was more of a materials processing effort.
As you talked about, like how these tiles and all these other protective measures are very brittle and you have to treat them very, very nicely. When we test them to prepare it for the shuttle itself, like, were we able to get to the same heights as like you would have in an actual shuttle launch, or how did testing these materials occur?
So with a lot of the tile and carbon-carbon, you can test them in arc jets, right? So you basically, it's like a flamethrower, you're put in a flame on the material in a controlled circumstance. That gives you some data, but not all of the data, because that's not in an airstream. That's in a vacuum in a still case. But it's one thing you have to figure out too, as a materials person, is how are you going to test the material to figure out if it works? And sometimes as an engineer, we're like jigsaw puzzle people. We have to do a test over here to test one thing. You have to do a test over here to do another thing. And you've got to integrate that together. But the best way to test a system is to put it in the environment that you're going to need to fly it in. And so, for example, you've seen a lot of what SpaceX has been doing and Northrop's been doing with their cargo vehicle. Every time they fly a vehicle, they get data off of it to see how it's performing. And so ideally, if you really want to know how a material is performing, you do a full-scale test of it in the actual environment. And so in our case, in the space industry, that means flying unmanned vehicles and letting them come, re-enter to see what happens. That's expensive though. So when you design those kind of tests, you have to think really carefully about everything you're doing so you get all the data that you can.
I'd be nervous to be the engineer that gives it the okay, just in case anything went wrong, and it costs hundreds of millions of dollars.
It's why there's a huge team of people that do those things. Yeah.
Another area of interest that I have particularly is energy storage. And one of the critical resources on the space station itself is energy, because it keeps you alive, produces oxygen, produces water. One interesting point that you mentioned in previous conversations is a new type of solar cell packaging. How is form factors as well as space and energy so important when we talk about space travel?
Yeah, so let's just walk through that. It's a really good question. So we have to launch everything right now. We have to launch everything that we need in space, right? And so the space station actually took about 10 years to build, launching it a piece at a time. And so every shuttle that came, and the Russian launched some pieces on their rocket, brought another piece of the space station. So for example, if you look at that big truss on the space station, it holds the solar arrays. Those were launched as piece parts. And so the solar arrays had to fit, and the truss they were on had to fit in the shuttle bay, right? And if you launch things on rockets, they have to fit underneath those fairings of the rocket. So there is a volume limit that has a very specific geometrical constraint for how you launch things. So the space station solar arrays were basically accordioned down to sit flat during launch. And then when they were on orbit and they've been installed, they just sort of unaccordioned them, if you will, and they unfolded them and sent them out. So some people are looking at solar arrays that you can sort of roll in like a carpet. So it's a much more efficient way and a much less complex way to unfold them. Because, you think about the complexity of designs that you have to come up with to fit certain constraints, right? And so those would be hugely beneficial to have solar cells that can be flexible. They don't have to sit in a plane, because that was what was driving some of the design of the solar arrays, because, they have to sit, the cells have to sit flat. You think about the circuitry involved in there, right? You've got the protective material for the cell, then you've got the cell, the material that takes the photons and turns it into electrons, and you've got material that grabs those electrons, and connects it with wires and connects it to batteries. So it's a whole ecosystem inside what looks like just a simple gold little solar cell with multiple layers of materials, and then so how can you take all that and make it much more easy to launch and to unfurl? So these are some of the things that are happening in solar cell land.
And then how does, I guess, the solar cell efficiency differ on the space station versus like solar cells that you see here on Earth?
Well, so the solar cells that are on the station right now were launched and designed a couple decades ago. Right. So, but they were the state of the art at the time. And so they're actually pretty good, and they haven't been degraded as much as we thought that they were going to be over time. So I think they were running about 20%, but don't quote me on that because I haven't looked into it for 5 or 6 years. So they're actually pretty good. Now the state of the art on the Earth, I think, has changed. But I think actually, again, don't quote me on this, but I heard that they might be thinking about replacing the solar, like upgrading the solar cells on the station, which is good. But back to, I think David, assumption you mentioned is power is an issue on the space station. You need power to do everything. So when you were designing the space station, they had to think about how much power we're going to have the vehicle provide. And then X amount of that power is going to be used just to keep the station alive, and keep the crew alive. And then the rest of it is going to have to be used for science experiments and things like that. And so they had to size the solar arrays and combine with what were the materials that were available to build the solar arrays out of, and how efficient could they get them, because that also affects the size of the solar arrays. So all of these factors play together, and the materials, again, are at the bottom of it all. If you have an inefficient solar material, you got to have a bigger solar array.
And another part is that for the energy storage, so I would assume the batteries were installed at the same time as the panel. So decades ago, battery technology has been doubling in progress, like every couple of years at this point. We're having rapid growth from lead batteries. So how have they replaced the batteries, or how exactly has that happened?
Yeah, that was a planned upgrade. Okay. Right. So they've been replacing them. So there's sets of batteries for each sets of two solar arrays. And so they've been slowly, I think they just finished the last one last year. So they have been doing that. So again, when you design something, you have to think about things like that, right? And you have to design in that upgrade. So you have to think about how all that, what technology, like computers is another one, what technology is likely to change, and how can we design in this kind of upgrade and maintenance. So they have been doing that.
And then another point is that batteries are also dangerous. I'm sure we've all heard about batteries catching on fire, and I assume that fire would be even more dangerous in space. How is safety handled on the space station in general?
Yeah, so I think safety is a huge issue, and that starts with the design, and then how things are tested, and then how they're operated. So the batteries sit actually outside on the truss near the solar arrays. So each pair of solar arrays has the batteries that service it, right out there. There aren't those big batteries are not inside. And then you have to design those batteries to withstand the vacuum of space and the thermal fluctuations that you're going to get whether you're on the sun side of the planet or the shade side of the planet. And you're going to have to design in protections for if they see a short, or if there's a short that starts to develop, and there's somebody in the control center whose job it is to watch the electrical power system and make sure it's all behaving correctly. So you've got layers of things from the design down to the manufacturing and the testing, and then the operations.
Okay, so then with the space shuttle being such a complicated system, and one big milestone that we're all looking at is sending humans to Mars, what do you think is the biggest constraint that we're facing to achieve that milestone?
No, quite honestly, it's budget. but technologically speaking, I think we're learning a lot about Mars because of the rovers. I mean, there's several rovers roaming around right there. Learning about the dust storms. For example, are the dust storms too severe that solar won't be an effective power source there? And if that's not the right power source, what do we use? How big of a factor is all the dust? What is the Martian soil made out of that we can manufacture things with? Can we manufacture fuel? These are the kinds of questions that we need to answer. And some of this type of research and experimentation and technology development we can do in the lunar area, which is why you hear a lot about NASA going back to the moon. So we can take do some trial runs there, some of these operational paradigms and some of this technology. So the moon's only 3 days away. Mars is 6 to 7 months away, depending upon when you launch. And so practicing in your backyard makes a lot of sense. So we have a chance to wring out some of this technology in our near neighborhood before we take the long trip across the ocean, as it were.
Yeah, I never knew that the dust storms were that bad. And because the rovers are solar panel powered, do they have ways to clean themselves, or how does that work?
I don't think that they do. And so it
Mhm.
just degrades over time, the
Mhm.
amount of power that they have. And could be the storm comes through and cleans for it, right? So I think they're seeing a little bit of everything, but over time you'll just get a slow power degradation.
And
And
is
they'll
that what
start.
happened with the rover that died and everybody was really sad and we had like a 21 gun salute or something for it?
I don't remember. You probably have to go check online. But think about the like the Voyager spacecraft, right? Are you
Mhm.
familiar with them? They launched in the 70s. They're now out of the solar system. Their power source was a very small piece of nuclear material.
Hmm.
That provides power as it decays, and it decayed past its half-life now. And so there's not that much power left on the Voyagers, but it's enough for them to check in with those spacecraft occasionally. I think there's like one instrument that's working on those. So how you create large amounts of power in some of these unusual environments is really important. Is fission possible? Is nuclear power possible? What are our other options as you get further out in the solar system, especially?
Going to another question one of our followers had on Instagram, Ibrahim was wondering if you could talk about material synthesis and microgravity environments. I know we talked a little bit about how
Mm-hmm.
the properties change, but when we take that concept further into space manufacturing, how would microgravity enhance manufacturing? Would it make it cheaper? I know there's a cost barrier to getting it up there, but let's say if we could get it up there, what are the benefits?
Well, that's the question of the day, right? And I think that's something that your generation will be working on a lot, because there's a huge effort right now, and there has been for a while, but it's really become much more widespread as we look to go back to the moon and really think about tackling Mars. Is what can you do with the materials that are there? What can you make out of them? What kind of resources are there? Because you don't want to have this huge monster logistics tail that comes all the way back to the Earth. And so what can you manufacture there? And then there's other people looking at what are the available materials if you capture an asteroid and mine the asteroid. There are other people looking at 3D printing in space. I think manufacturing in space is not yet a thing, because it's not just a matter of what materials it might be beneficial for, but also just building the manufacturing plant
Mm.
as well, right? And how you power it? How much power do you need? Is solar enough? Are the solar cells, are those materials efficient enough? Do you need a certain amount of stability? Is it human tended? Is it manned? Can it be totally autonomous, or do you need people there? I mean, I think we have a lot of those kind of questions to answer. And David, to your point, what's the business case? I think as we get more and more activity off the planet, it will make sense to make things up there that we use up there and just launch raw materials if we need to, because that's a lot more effective. But we're not there yet. I think these are problems that you're going to have to solve, your generation.
So you mentioned that we'll have potentially more activity as we go to our backyard on the moon. And so do you see that there being a parallel there where more in-space manufacturing is needed as we send more people to the moon and practice those experiments?
Yep, like I said, people are already working on how can you make a habitat out of lunar regolith, because if you can make a habitat like bricks, make bricks, make a habitat, that also provides you some shielding from the radiation. It's another materials problem, right? You've got a lot of radiation up there. We're shielded on the space station a little bit by the Earth's magnetic field, but you go out to the moon and how you need other kind of shielding. So what kind of materials can you use, or what kind of designs can you use to help shield humans from some of that really bad radiation? And so there are people looking at the regolith on the moon. It's like, and by extension, Mars, can we build big bricks and, make habitats, or at least line, our aluminum shells, if you will, with these bricks to help shield us? And how would you make the bricks? And would it be autonomous? And what kind of machinery do you need? What kind of materials does the machinery need to be made of? You can just, the questions go on and on and on. And there's a lot of people looking at this, but this, I think, will be something that comes online as you guys, start your careers and move into them. It's pretty exciting, actually.
For sure. What have been the findings so far, do you know, in terms of how materials in space, like the asteroids or whatever, how do those properties differ from some, materials that we see here on Earth?
Well, I mean, asteroids come in many different flavors. And so it's really a matter of extracting the raw materials to do stuff with it. It's not like the materials themselves are different, although the abundance is different based on, I mean, depends on, again, what asteroid you're looking at, but it's more a matter of, as opposed to having to launch all these materials out of Earth's gravity well, you can get them there already. And that changes your business case and that changes your cost. And so that's another thing. And there's sometimes in some asteroids, there are some metals and elements that aren't as common down here. And so that's another benefit. But again, you have to find the right asteroid, which is a whole nother ball of wax, right?
And I guess just theoretically, in my mind, elements that have like less protons, less neutrons are like more statistically possible to form due like they don't need as many things to happen to them to form. So if, for example, we take a bunch of asteroids, but things like lithium and sodium, things that are lower on the periodic table, be more prevalent than like uranium and things higher on the table?
It just depends upon the asteroid. I mean, there's a lot. I don't know if you could find uranium up there as much, but some of the rare earths, iron is a big one. There's a lot of iron, but just depends upon the asteroid. But I'd say probably like in the middle of the periodic table.
And so you mentioned in a previous conversation that, there is 3D printing in space going on right now, mainly with polymers, and then potentially moving on to metals in the near future. What does that future of in-space 3D printing look like to you? And what steps could MSCs like David and I take to achieve that vision?
Right. So that's a thing, 3D printing in space. Like a lot of these people who are looking at how to make bricks and other things, that the printing, remember, printing is a processing technique, right? And so you have other processing techniques where you like to make bricks, for example, where you can compact the brick, densify it, and then sinter it or fire it and heat it. So it all kind of fuses together, right? So there are different techniques, but 3D printing is handy because you can make lots of different shapes, right? Now the trick is, and there's a company called Made in Space, which is really at the forefront of this, but they're not the only group that's doing it, but they were the first ones to get a 3D printer on the space station, probably, I don't know, 7-8 years ago with polymers, and really understand, again, remember we talked about how water and fluid has different properties. So you've got to figure that out, right? What's, you're printing from are you printing from a fluid, or are you printing from a thin strand? Once you melt it to deposit it, what's all of the fluid dynamics that you have to deal with, or the surface wetting or things like that. They had to sort through that. Then putting a 3D printer outside is a whole nother interesting factor, because you've got the temperature changes, right? Everybody knows that when things get hot, they expand, and when they get cold, they contract. So if you're trying to deposit something, using a 3D printer technology, and your thermal environment is changing on you constantly, what does that mean for the material that you're laying down, right? So, and that could change metal to polymers as well. Plus you're in a vacuum. And how's that affecting your material? What's the vapor pressure? And so these are the kinds of questions people are asking. And then another group of people is also looking at, how can you 3D print a structure that's bigger than the printer, right? If you think about your standard 3D printers, it's a box and you make something in the box. Well, if you're trying to build a beam to hold a solar array, for example, or even an antenna, some big circular antenna, you can't put it in an enclosed box. It's bigger than, so there's a group, at the time they were called Tethers Unlimited. I'm not sure if they still have that name or not, because I haven't followed them for a couple of years, but they were creating a device that kind of works like a spider, with the the printed part coming out of one part of it and a few legs that can scuttle along the device that it's printing, right? But again, you have to think about what are the materials, how structural is it?
Mm-hmm.
You're printing out in the vacuum space with thermal environments. So how's that going to affect your final product? So these are all the questions that people are looking at right now, and I don't have the answers.
I didn't even think about trying to like print something bigger than the box. That's just never occurred to me. And I don't think it'd be very feasible to do like a jigsaw puzzle in space with like a giant space antenna or something like that. So that's a fascinating issue.
But think about it. If you're in microgravity, the whole issue with loads is different, right? So a beam that you build in space to support something that's in space is not going to have to be as beefy or as massive as one that's having to work under the forces of gravity, right? So the materials can be completely different for the same application, whether it's on orbit in microgravity or here on Earth.
My initial thought was, why not just print components within that 3D printer? But maybe that's kind of maybe a weak point when those components are welded together. Would that be a correct assumption?
Well, actually, here's a conversation we can have about this. So I did some soldering experiments while I was up there as part of some soldering. So you remember how a sphere, I talked about liquid wants to form a sphere. So what's solder? Liquid metal, right? So when you try and solder things in space, you have to be really careful about how you're doing it, because the solder wants to just ball up and not wet into the joint, right? So the thermal gradient you're applying to the solder and the mismatch between the solder and the material that you're soldering becomes way more important, right? And so if you think about, welding components together or doing these other kinds of things, there's a whole different dynamic in microgravity because of this surface tension and wetting forces and how they affect. So that would come into play if you were trying to put components together. But I don't think we're at the point where we can 3D print those kinds of complex systems at that level yet, even on the Earth. I mean, maybe somebody's doing it somewhere in a corner that I just don't know about, but that's a pretty complicated 3D printing. Although people are looking at functional materials, how do you 3D print a material that's a conductor on one side and an insulator on the other, right? And what's that gradient as you change those material properties? So there are people looking at all these things, but I don't know. I don't think we're at the point where someone can just push a button on a printer and a satellite comes out like totally functional, right?
But yeah, so you've quite literally had an out of this world experience that we've really enjoyed hearing about. And now your next step is joining Georgia Tech and being a part of an aerospace engineering, material science and engineering, and international affairs programs, where you will focus on providing leadership and mentorship to students like us. What kind of motivated you to return to tech? And what advice do you have for MSEs who want to strive to go where you've been?
Well, I've had a heartbeat with tech ever since I graduated, serving on different boards, and I've been very engaged with the campus. And I really enjoy working with students. When I was running the American Institute of Aeronautics and Astronautics, that was hugely fun. And of course, I worked a lot with students when I was an astronaut. And so having the opportunity to come back to campus and working with students was super attractive. I mean, you guys are all brilliant and you're doing amazing things. And it's just fun to be around all that energy and just see what you can accomplish. I really enjoy that. And I think for anybody listening, I think that the real key is, and this is what I did, is I followed my passion, because you don't know what you don't know when you're first starting out. I started in physics and I was going to go through and get my PhD in physics because that's all I knew. And then I got interested in electrical engineering. And then I got fascinated by materials. So I just kept following my interests and following my passion. And if you do that, no matter whether you're in materials or whether you're in engineering or no matter what you're doing, if you're following your passion, you're going to be fine, and keep yourself open to new experiences and open to new interests, and don't be hesitant to follow those as they come up, because life is a lifelong journey of learning. And I think that's, one of the things that if you look across everything that I've done in my whole life, it's I've perpetually been a student, perpetually have learned new things. And if you have that kind of an attitude and are willing to be that open-minded and adaptable, you're going to have a wonderful journey.
I think there's a quote that I remember where it's like, once you stop learning, you stop living. And I think that kind of speaks to exactly the advice that you gave, and the idea to keep your doors open is definitely very valuable.
Absolutely.
Well, thank you so much, Sandy, for coming on to the show today. We really learned a lot about materials in space and just loved hearing about your journey to get there and your time in this in the space station. So thank you.
You're welcome. I enjoyed the conversation.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. If you want to meet other passionate material scientists and engineers, join our Discord community using the link in the description. If you have any feedback for us, we would love to hear it. We want to grow this show with our community's input, so comment below with your thoughts on this episode and what topics you want to see us cover next. We'll see you very soon, and in the meantime, go change the world.